Okay, so I'm going to do these three projectile motion problems now, and then I'm going to call it and go to bed and sleep. And you guys know that no, this is not everything you need to know, because there's still vector valued equation stuff you have to understand. There was the question about the hawk who was trying to catch a pigeon. You have to understand that. There's a question about a tortoise and a hare that were racing each other to some point. You have to know how to do that. But for vector valued equation stuff, it's just going to be equations of lines, and it's always going to just be like, do they crash into each other, or it's going to be who gets to a point first. It's going to be one of those two questions. So you can figure it out. So let's do this. It says Stuart shoots an arrow straight up from the top of a building with initial velocity of 245 feet per second. The arrow leaves from a point 200 feet above the ground. Alright, so honestly, the easiest part of this is probably part B, that says use parametric equations to simulate the height of the arrow. So in part B, you know that you would say, okay, x equals the initial velocity, 245, times the cosine of the angle. Now if he's shooting it straight up, then that's 90 degrees, times t. But hold up, isn't cosine of 90 just 1? I mean 0. I mean 1. I mean 0. It's 0. So x is just always 0. And then y is going to be 245 sine of 90 times t minus 16t squared plus our initial height, which is 200. But again, isn't sine of 90 just... Why am I so bad at this? Sine of 90 is actually, that's the one that's actually 1. So your y equation is 245t minus 16t squared plus 200. And your x equation is just constantly 0, which should make sense because the path of the arrow here is essentially that from wherever the dude's standing, he's at an initial height of 200, but he just shoots it straight up. So up it goes, and then down it comes. And so the x is definitely going to just always stay 0, but the y is going to go up and come back down. So now that we've done this, let's go back to part A. In part A, they want an equation that models the height in terms of time. Well, basically, just take your y equation. Instead of y, maybe say h of t. But the height in terms of time would just be 245t. Oh, God. So this equation is doing the... Well, this equation would not be the same graph. The graph of part A, remember here I'm actually modeling x against y. Here we're modeling time against height. So that would actually show a real parabola. Alright, but that's it for A and B. C says use parametric equations to graph height against time. Okay, we've got a calculator, so let's just plug into it. We make sure that we're in parametric mode. We go to y equals. I got a bunch of crud in here. Use parametric equations to graph height against time. Okay, I don't love this. I'm starting to feel a little weird. Alright, I think we would want x to be t, so that we see time going by. And then we would let the y equation be the same old thing, 245 t minus 16t squared plus 200. Now if we hit graph on a decent looking window, so if we're letting t be time and x is time, then we would only want to go out to the 10 seconds. So -2 to 10. And our height, we're probably going to go pretty high. Let's go all the way to 1,000. That's strange. Okay, so apparently it stays in the air a long time. So let's go up to 20. And we gotta go a little higher. Okay, there you go. So this thing is now modeling height against time. So the x-axis here is time. Alright, we did it. How high is the arrow after 4 seconds? If they're just giving you a time, then I would say go to calc and choose value and just enter 4. And they're going to show you that when time is 4, we're at a height of 924. And that's it for part D. Then they say, what's the maximum height of the arrow? Well, in parametric mode, we can't find the max. We don't have that option. But we know that algebraically, we can find it. So for part E, we know that our max occurs when time is equal to -b over 2a, which is -245 over 2 times -16. So that's positive 245 over 32. And 245 over 32 is 7.65 blah blah blah. I'm going to go ahead and store that as A, like I always do. Then I'm going to go second calc value, plug in A, and we should see a point right at the tippity top. We do. And so we see that our maximum height occurs at a time of, what is the maximum height? When does it reach its maximum height? So to answer part E, you would say the maximum height is 1137891. Feet. And you can't see this, I know. But there it is. So that's the max height. And it occurs, oops. It occurs at t equals, I mean really it's the 245 over 32. So let's just give that as an answer. And let's see if that's reducible. Nope, so 245 over 32. So you can see that I don't expect your maximum height to be exact, because your maximum height, well, whatever. Your maximum height usually is going to involve a trig expression, and it's going to be gross. Your time is pretty easy to calculate, so I typically do expect you to give that exact when you can. So there. Lastly, it says how long will the arrow be in flight before it hits the ground? And this is kind of a dumb question if you stop and think about it, because it says Stewart shoots an arrow straight up from the top of a building. So, I mean, I guess we're pretty obviously assuming there's no wind, right? because wind would blow this thing off course. So how's it going to hit the ground if it goes straight up and down? Isn't it going to just hit the building again? Alright, well, ignoring all that stupidity, you know that what they mean is just how long is it going to be until y equals 0. And I don't feel like doing quadratic formula. We certainly talked about that. So what we should do is go back to function mode and just enter a rectangular equation for y, which is still 245t minus 16t squared plus 200. Yeah, and we just want that point right there. For y's, where'd you go, y's? I'm going to go down a little more just so I can see it better. But if I want that point, then now that I'm in function mode, I can go second calc, and suddenly 0 is an option, so I choose option 2. They want a left bound, so I'll just go to the left of that point that I think is my x-intercept. Okay, and I'll hit enter, and I'll go to the right of it, and I'll hit enter, and then I'll try to go right on it. And that's it. It says it's going to take 16.089 seconds before we hit the ground. $16.089. There you go. So that's that for that problem. So that problem covered maximum height. It covered height at a specific time, the 4 seconds, and it covers how long we stay in the air. So that question actually covered pretty much everything you need to know, but we'll do the rest anyway. Like this one about kicking a field goal. It says Spencer practices kicking field goals 40 yards from a goalpost with a crossbar that's 10 feet high. If he kicks the ball with an initial velocity of 70 feet per second at 45 degrees with the horizontal, will Spencer make the field goal if the kick sails true? Alright, so for sure we want to write our parametric equations, which will be initial velocity, 70, times the cosine of our angle, which is 45, times t. And then our y equation will be the same thing, 70 cosine, sine, minus 16t squared. That's accounting for gravity, plus our initial height. But when you kick a field goal, you get to use a little t that holds the ball, but it doesn't really give it any extra height. So I think we're assuming the initial height is 0. Okay. So how do I do this? Well, I would certainly enter my equations into my calculator in parametric mode. Okay, so that's that. If I hit graph, it's going to look like crap, so you got to go fix your window. Our t of 20 seconds is way too long. There's no way a kick is going to take that long. 10 is still too long, but better too long than too short. The x is horizontal distance traveled, so if we're only trying to go if that's 40 yards, by the way, don't forget, we have to convert that times 3. There's 3 feet per yard, so this needs to be 120 feet. So change that real quick. So now when you go to make your window, your x's are going to want to go out, I don't know, -40 to, I don't care, 200. 200's too far, but I don't care. And I don't know how high this is going to go. Probably not very high. Yeah. All right, Mr. F's not feeling great. 100. 100 seems fine. And that looks good. The only thing I don't like about it is my scale. Let's go by 10 and 10. Just so the axes don't look so weird. Okay, fine. There you go. We did it. Now it says what? With will he make the field goal? So this is that problem where, assuming the kick is good, it would come up, 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 go over the goalpost, come back down. So what do we know? Again, what we know is the distance traveled by the ball. So for every point on the trajectory of the ball, there's a time, there's an x, and there's a y. And for this problem, what we know is x. We know that x is 120. So your plan is to use the 120 to find t, then use the t to find the height, and then to decide if the height of the ball is higher than the 10 feet or lower than the 10 feet, and that's it. So if you take your x equation and set it equal to 120, then you can solve for the time, and you can do this by hand, and you must do it by hand, because all you're going to do is divide by 70 cosine 45. Cancel, 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 cancel. So we find that the exact expression for our time, and by the way, you can divide these both by 10 to simplify, is 12 over 7 cosine 45. So I do expect you to give me that exact expression. And then you could also give me a rounded off decimal. You could do both. But make sure you give me the exact expression or you're not getting full credit. So I'll just quit to my home screen and I'll do 12 divided by parentheses 7 cosine 45. And it's 2 point blah blah blah. So I'm going to store that before I forget. 2.424. Okay. So that means now that I just go back to my calculator and we're going to go second calc value and just plug in the value of A that we stored. Press enter. And so we can see that we've gone 120 feet after 2.424 seconds. And at that time we're at a height of 25, which is plenty high enough to go over a 10-foot goalpost. So make sure that just your answer to me brings all that together. Make sure you mention the x, the y, and the time. So you'd say something like the ball has gone 120 feet after 2.424 seconds, and at that time is at a height of whatever it said, 25,959. So I'm saying it's at a height of 25.959, which is higher than the crossbar. So it is a field goal. Exclamation point. And I know that you can't see that, but now you can. So just make sure you write me a good sentence, because since you don't really have to do any algebra to solve this problem, I need to make sure that the concepts are there. So make sure you mention, I know the horizontal distance to the field goal, and I know the time it takes to get there. and I know the height when I'm there, and I know to compare that to the height of the crossbar. So not a bad idea to include that number too. Crossbar is only 10 feet. So that makes it real plain that you know that the 25.959 is higher than the 10 feet. That's why it is a field goal. But that's that. And then there's what, one more of these and then I can actually go to bed. So one more. Okay, so I mean, number 87, this has all the same, it's the exact same as 79. In 79 we had to find the maximum height, we had to find the hang time, so it's the same. I'll do it again anyway, just in case, but it's the same. But you're going to write your parametric equations, so 85 cosine 56 t. Alright, a place kicker should have some kind of initial height. A place kicker kicks a football downfield, the ball leaves his foot at the da-da-da-da-da-da-da-da-da. Alright, I guess not. Place kicker. Okay, so I don't know. I don't know a ton about football. But if this guy was punting, if he was a punter, then he's holding the ball and he kind of drops it onto his foot and there would be some initial height. I guess a place kicker kicks it off the ground. So I guess it's 0. Whatever. You guys would know to think about that, I hope. But we know now that if we want to find the maximum height, then the maximum height always occurs at a time that equals negative b over 2a. And for our problem, b is the coefficient of t. So 85 sine 56 divided by 2 times negative 16. So the negatives cancel. You get 85 sine 56 over 32, which doesn't look like it's going to reduce to me. 85 and 32. Let's just make sure. Yeah, doesn't reduce. Okay, so that's that. So what is 85 sine 56 divided by 32? 2.202. So store that as A. Alright, and then you can tell me that this number is approximately, whatever I just said, 2.202. Okay, make sure you're giving me the exact expression. I want that more than I want the decimal. Now that's not the maximum height, of course, that's the time when the maximum height occurs. Now I've not entered these equations yet, so let's enter them. 85 cosine 56. Okay, and again, no initial height, I guess. So go to calc, value. Yep, so that's showing us a little cursor at what definitely looks like the maximum height to me, so I feel good about that. And it's telling me my maximum height is 77. Now, they didn't care about how far had it gone horizontally, so the 104 you can ignore. We just want the 77.590. So that's it for A. And the part B, the hang time part, that's the part where we go back into function mode. You're trying to find the x-intercept, but you can't find it in parametric mode. There's no great way to get to that point because if you hit second calc, the option's not there. So just go back to function mode and quit, clear. Get that out of here. Type in your new equation, which is 85 sine 56. Press graph. So here the graph got messed up because we're now graphing height against time. So you better change your window to just go from like -3 to 10. We just want those seconds. And then that's decent. That doesn't have to be any better than that. So now you can go second calc, and you want the 0. The x-intercept is called the 0, so choose that. And you want your left bound. I'm already left of it, so I hit enter. Go to the right of it, hit enter, and then give me a guess. There you go. Yeah, so the x here is time. 4.404. Alright, so I do want to point something out to the kids who think they're smarty pantses. We did kick this ball off the ground, right? So the fact that we kicked it off the ground meant that the x-intercept was a 0. So when it came time to find the other x-intercept, we should not be shocked to find that it's just the time to our maximum doubled. We already knew that our maximum occurred at 2.202. I'd like to think somebody noticed that 2.202 is just half of 4.404. But you know that's not going to work for any question that has an initial height. If I had an initial height that was fairly high, then I'm going to achieve my maximum height, and then the point symmetric to that is going to be here. And we're going to hang in the air for a little bit longer before we hit the ground. So don't assume that the hang time is always just the maximum time doubled. It only happened here because we had that initial height of 0. So don't screw yourself by trying to get too cute with it. Although if you know that your initial height is 0, then get cute with it. You can say, I know that the hang time is just the time to the height doubled because of the symmetry of the graph. Alright, hope this helped. See ya later.